Hi all, I am Chitralekha from the Department of Artificial Intelligence and Data Science, S.A.E. Engineering College. In today's GATE coaching class, I am going to talk about binary search tree. Before knowing what is binary search tree, we should know certain terms in data structure. So, the first one is what is data structure. The second topic we are going to discuss about types of data structures, and then we are going to see what is a non-linear data structure and what is a tree, what is a binary tree, and what is a binary search tree. These are the topics we are going to discuss in today's class. What is a data structure? It is a way of organizing and retrieving the data along with its relationship. That is data structure. Here we are not only going to store and retrieve the element, but also the relationship among those elements. That is data structure. It is widely classified into two categories. One is primitive data structure and another one is non-primitive data structures. We will see what is primitive data structure. Primitive data structure is nothing but they are already built-in functions. Primitive data structures are integers, floats, characters and pointers. These all are the primitive data structure. Then what is a non-primitive data structure? Non-primitive data structures are derived from the primitive data structure. It is widely classified into two. One is linear list, another one is non-linear list. Linear lists are array, linked list, stack and queue. These all are linear linked list, whereas non-linear linked list are graphs and trees. So okay. Next, what is linear linked list? They are stored in a structured manner, like it is stored one after the other. That is, it is stored in a sequential manner. That is linear list, whereas non-linear list are the data or the information which we are going to store in a non-linear data structure format. It will be stored in a hierarchical manner, that is one after the other. For example, for linear, the data are stored one after the other, that is in sequential order, whereas in non-linear, data are stored in hierarchical manner. That is the major difference between primitive and non-primitive data structure. That is linear and non-linear data structure. Now we will see what is tree. Tree is one of the non-linear data structure. Okay, a tree is nothing but a non-linear data structure that are stored the data in a hierarchical organization. Here we have certain features like the elements are stored as successor and predecessor. Successors are nothing but the child node and predecessors are nothing but the parent node. In trees, every element is stored as a node and those elements are known as parent and child, that is predecessors and successors. The basic terminologies used in trees are, first one is here every element, whatever data or whatever information we are sharing in data structure as tree means, we will tell it as a node. Okay, first is child and parent. Every node except the root node has only one parent. That is the first thing. Second one, a node can have an 0 or more children. This is a basic terminologies of trees. Next, what is a leaf? Leaves are nodes without any children. Like there will be a parent node followed by a child node. Without furthermore child means then that nodes are said as leaf nodes. Next one is sibling nodes. Sibling nodes are nothing but their parents will be the same. What is a path? The sequence of node or edges which are from one to another. That is the difference of a path. Next one is the length. The number of edges on the path is said to be the length of a tree. Next one is the depth. How far the trees are hierarchical. That is known as the depth of the node or depth of the tree. Next, what is a binary tree? Here we are going to see what is a binary tree and binary search tree. First we should know what is a binary tree. A binary tree is nothing but a parent with a maximum of 2 children. That is said to be a binary tree. A binary tree is a collection of nodes that consist of root. Root is nothing but the parent here, and other subsets. Subsets are nothing but the child nodes here to the root points, which are called as the left and right subtree. Here we have, for example, 1 is the root node, followed by 2 and 3 are its child node, and 2 has a child of 5 and 6. Maximum of 2 child is processed in a binary tree, not more than 2. For example, if you consider this one, this is not a binary tree because it has the maximum of 3 child here. So it is not considered as a binary tree. Still this part it is considered as a binary tree, but as a whole it is not a binary tree since it has a maximum of 3 children. Always binary tree should have the maximum of 2 children. The difference between binary tree and binary search tree is nothing but in binary tree we will only concentrate on the number of child present for a parent. That is, a root node should have maximum of 2 child, whereas in binary search tree the same criteria is applied. That is, a binary tree should also have 2 child nodes, but the left subtree, this is the left subtree and this is the right subtree. Okay, the left subtree should always less than the root node and the right subtree should be always greater than the root node. That is the major condition for a binary search tree. But in binary tree we only concentrate on the parent node and the corresponding child node, but it has to be only 2. Whereas in binary search tree the same condition as that of binary tree, but one more condition applied here is that the left subtree should be lesser than the root node or parent node and the right subtree should be greater than the root node or parent node. Here, what are the standard operations performed in binary search tree is insertion, searching and deletion. We will see one by one. First one is searching technique. How the data are searched in binary tree is that if I am giving a value, I will be searching it into a tree. My binary search tree will be like this. Okay, if I want to find 5 in my binary search tree means I will be traversing from root to the leaf node. Leaf nodes are nothing but the nodes which does not have any children. That is said to be the leaf node. So I will traverse from root to child node or leaf node. Okay, first I will traverse 9. I will compare my value 5 with 9. What I am going to search is 5, so I am going to search or traverse or compare 9 with 5, which is greater. 9 is greater, so I should traverse through the left subtree. Since the searching element 5 is less than the root node, I will be traversing through the left subtree. So I will traverse from 9 to 4 here. 9 to 4, I will compare my searching element 5 with 4. I will compare both the elements, which one is greater. My searching element 5 is greater, so I will be traversing to the right subtree of node 4. Here I will be traversing the right subtree of node 4. Okay. Next, I'll traverse to the right subtree of node 4, I mean this parent. Again I'll compare with 7 and 5. The searching element is 5 for me, right? So I'll search with 7 with 5. Which one is greater, 7 or 5? 7 is greater. So I have to traverse the left subtree of node 7 because 7 is the parent node here. So I will be traversing the left subtree of node 7 and I have found my element here. The searched element 5 is found in the left subtree of node 7. This is how searching operation is performed in binary search tree. This is the syntax or this is the routine of binary search tree. I will check my first condition. If root is equal to null, I'll return as null. Or else if my number or an element is equal to root of data, then I'll return root of data as my number or an element. Next, I'll check my condition whether or if my number is less than the root of data, means I will return search root of left. That is the condition here, right? In binary search tree, whatever element or whatever information we are giving, it should be lesser means we should search in left subtrees of the binary search tree. This is the condition. The another condition is if the number is greater than the root of data, we will be returning the search in root of right. This is the general routine for binary search tree for search operation. Next, insertion. If I want to insert an element, a new element into already existing binary search tree, means I should compare the element which is going to be inserted into a list with the root node till the leaf node. The same condition. If my node is equal to null, means I'll return my create node as data. If my data is less than the node data, means node of left is equal to insert node left of data. I'll insert my new data into the left subtree of the binary search tree. When my data is lesser than the root node, then I will check another condition. Else if my data is greater than node of data, means node of right is equal to insert node right comma data. Here what I am going to do is the same process. I will check the element what I am going to insert into the tree. I will check with the root node. If that insertion value is greater than the root value, I will directly insert it through the right subtree of the binary search tree. For example, I am going to insert element 5 into this list what I have given. My list consists of 9, 4, 2, 7, 11, 15 and 8. Here the first condition is satisfied, that is it is a binary search tree with the maximum of 2 child. It may have 1 child but it should not exceed 2 child. That is the condition of binary search tree. The first condition is satisfied here. My second condition is the smallest values when compared to root node should lie in the left subtree and the largest values when compared with the root should lie in the right subtree. Now I am going to insert the element 5 into the tree, right? So I will compare 5 with 9. 5 is lesser than 9. Lesser than my root node, so I will traverse through the left subtree of this binary search tree. Once I traverse through the left subtree, my next value, my successor value is 4 here. Okay, when 4 is compared with 5, 5 is greater than 4, so I have to traverse through the right subtree of node 4 here. Okay. So after reaching 4, 5 and 4 are compared, 5 is greater than 4, so I have to traverse the right subtree of node 4. Next, I will compare 5 with 7 here. Okay, when comparing 5 with 7, 7 is greater than 5, so I have to traverse through the left subtree of 7. Okay, this is the condition. Once I reach the left subtree, I will check whether there is any data or element present or not. If it is not present, means I can directly insert 5 under node 7 as a child node. This is the process of insertion in binary search tree. Next one is deletion. To delete an element from the binary search tree, the user first searches for an element using the search operation. Through search operation only, deletion operation is performed in a binary search tree. If the element is found, what we done in searching, we'll compare the element which is going to be searched with the root node. If it is smaller, means left subtree. If it is larger, means right subtree. This is the way we process, right? For deletion, if I am going to delete the node 5, means I'll traverse through the left subtree and I'll compare here. If it is greater, means I have to traverse the right subtree and then I'll reach my element which I am going to get deleted. So this is how deletion is performed in binary search tree. These are the basic operations performed in a binary search tree, that is searching, insertion and deletion. certain questions regarding binary tree and binary search tree. What is a complete binary tree? The first option given here is each node has exactly 0 or 2 children. This is not a binary search tree or a binary tree. We are asking what is a complete binary tree. The next option is a binary tree which is completely filled with the possible exception of the bottom level, which is filled from right to left. That is your second option. Your third option is a binary tree which is completely filled with the possible exception of the bottom level, which is filled from left to right. The fourth option is a tree in which all nodes have the degree of 2. In trees we won't follow the degrees, in graphs only we will follow the degrees. The fourth condition is valid here itself. Now we will see the answer of this question. The answer of this question is C, because we will be checking whether the complete binary tree holds all the values in it and it travels from left to right. That is the condition of a complete binary tree, that is smaller value to a greater value. So left to right is the proper term defined for complete binary tree. The next question is the number of edges from the root to the node is called dash of the tree. As we seen in the basic terminologies, the number of edges from the root to the node is called dash of the tree. What will be the answer? The answer is nothing but the depth. How far the tree is being hierarchical, that is the depth. So the number of edges from the root to the node is called as the depth of the tree. Next question. What is a full binary tree? We have seen what is a complete binary tree. Here we are going to see what is a full binary tree. First option, each node has exactly 0 or 2 children. That condition is applicable for a binary tree. Each node has exactly 2 children. That is option B. Next option is all the leaves are at the same level. Fourth option, each node has exactly 1 or 2 child. Which is the right option? We will see. Each node has exactly 0 or 2 children is the right option of a full binary tree. We will see further more examples in the next classes. Thank you.